All right, in the first part of chapter 17, what we did was we looked at some reactions and we learned how to alkylate, nitrate, sulfonate, deuterate, an aromatic ring. We also looked at how to determine where the group got placed. Okay, whether it was substituted in the orthopara, meta, or orthopara or meta position based upon the group that was already there. Now what we're going to do is we're going to look at a couple of other reactions. And these reactions are just ways to put other groups on the ring. And then when we get done, we're going to look at some complex synthesis type reactions. So the first reaction we're going to look at in this chapter is called the Friedel-Crafts alkylation reaction. And just as the name predicts, it's going to put an alkyl group on the ring. So here's the reaction that occurs. We take an aromatic ring and we add an alkyl halide. So we add something like methyl chloride or methyl bromide in the presence of a Lewis acid. And the normal Lewis acid that we use is aluminum chloride if the alkyl halide is a chlorine, or we use iron bromide if the alkyl halide is a bromine. Okay? And what happens is it just puts the R group on the ring. Now that's all that happens here. Okay? The way this reaction works is very similar to what we've seen before. So let me just change this to a chlorine and add aluminum chloride. What happens again is that this RCl loses the chlorine to give me this cation and then AlCl4 with a negative charge. So the chlorine just moves over there. Notice that this is a cation. It's a carbocation. It's a positively charged carbon. The positively charged carbon is what acts as the nucleophile. So this reaction occurs by forming the carbocation. Now, it's a carbocation. It is a full-fledged carbocation. So if it can rearrange, it will rearrange. Okay, if it can undergo all those rearrangements we learned when we were doing SN1 and E1 reactions, it will still rearrange. So we have to realize that the alkylation reaction forms a carbocation. So this is the easiest way to form a carbocation. Now there's two other ways that are mentioned on page 1 of these notes that form a carbocation. The first one is to take an alkene. And I'm going to use this alkene. I'll draw it out in a little bit more detail. And we're going to react this with HF, hydrofluoric acid. Now we can think of the HF as being H plus and F minus. So if we think of this as H plus and F minus, notice this pair of electrons is going to come out and attach to the H. We saw this same type of reaction whenever we were doing the reactions of additions across the double bond. Now notice what's going to happen. The H is going to attach to this carbon to form this carbocation. Notice by attaching to this carbon, we add and we form the more stable carbocation. So the same thing is going to happen as what happened in chapter 8. We're going to get Markovnikov addition of the H. Now, normally what would happen is that the halogen would come in and attack the carbon. But because fluoride is so electronegative, it does not want to do that. So you're left with what? A carbocation. So the reaction of HF with an alkene forms a carbocation. And again, that carbocation is going to be my electrophile. So this is just a second way of forming a carbocation. We can also take an alcohol. Now, I'm illustrating this in my notes with this ringed alcohol, but I don't have to. Okay, and notice there's an H on there. And if we react this with BF3, now BF3 is a compound that we've already talked about once. I'm going to draw that out in a little bit more detail. Notice this boron is very electron deficient. It's already only got 6 electrons around it, but these fluorines are pulling electron density away from it. So that boron atom wants electrons very badly. Notice the oxygen has lone pairs of electrons and can donate it into there. When that happens, this pair of electrons goes back, and notice what we form. This carbocation and this BF3OH negative ion. Okay, we don't really care about this. Notice what we formed, a carbocation. So there are 3 ways to form a carbocation. You can take an alkyl halide and react it either with aluminum chloride or iron bromide to make the carbocation, or you can take an alkene with HF, or you can take an alcohol with BF3. All 3 of these methods do the same thing. They form the carbocation. And that's not really the important part of this. The important part is that that carbocation is the part that acts as an electrophile to do an aromatic electrophilic substitution. Now listen carefully. This reaction has some drawbacks to it though, and they're listed on page 2, and you need to know these drawbacks for this reaction. It only works with benzene, activated benzenes, or halobenzenes. So this reaction will not occur if the ring is deactivated. For example, if it has a nitro group already on the ring. Now, this is the only reaction so far that will not work. All the other reactions we talked about in the first section, they occur on deactivating rings. It's only the Friedel-Crafts alkylation reaction that will not occur on the deactivated rings. You get a carbocation. So if that carbocation can rearrange, it will rearrange to the more stable carbocation before adding to the ring. The third one is, if you add one group, watch what happens. Let's do this reaction. And let's suppose we added methyl chloride in the presence of AlCl3. What's the product of that reaction? Well, it's simply going to add an alkyl group, the methyl group, onto the ring. But remember, this ring was 25 times more reactive than this ring. So what we will get is we will oftentimes, remember this is an ortho para director, so we'll put another one in the para position. We oftentimes get polyalkylation reactions. Okay, so if we're trying to only get the monoalkylation product out of this reaction, sometimes that's hard to do. On the test, I will ask you to give me the monoalkylation product. Okay, but in real life, that's oftentimes hard to do. Okay, so there's some problems with this Friedel-Crafts alkylation reaction. But again, you will be using it in your synthesis later on. To avoid at least a couple of the problems that occur, we're going to do what's the reaction on page 3. And we're going to do what's called the Friedel-Crafts acylation. Now, the acylation puts an acyl group, ACYL group, on the aromatic ring. And here's what happens. We take an aromatic ring and we react it with an acid chloride in the presence of aluminum chloride. And what this does is it puts the acyl group on the aromatic ring. Now let's look at this for just a second. This acid chloride, let me put my lone pairs on here, reacts with aluminum chloride. We get the same type of carbocation, and I'm going to draw it like this, even though I know that it's going to be wrong. Now, that's exactly what happened in the alkylation. Except this carbocation, bringing a pair of electrons down, is resonance stabilized. This is actually the more stable resonance structure because notice we get octets for everybody and we have the most number of bonds. This cannot undergo rearrangement. So when we do the acylation, whatever the R group is, it can't undergo any rearrangement because notice it's not where the positive charge is located. So the first thing we can say about the acylation, and this is not in your notes, you need to add this to your notes, is that it does not have rearrangements. Okay? Also notice when we put the acyl group on the ring, it's a deactivating group. So therefore this ring is less activated than this one. So any more acylation will occur on this. So we only get monoacylation. Now, if we want diacylation, we have to add an excess of the acylation reagent. But we normally only get monoacylation. So this solves two of the problems with the alkylation reaction. Okay, now listen carefully. It doesn't say this in the notes, but this reaction still only occurs on activated benzenes, benzene itself, or halogenated. The acylation reaction will not occur on deactivated rings. That's going to be important in just a little bit. So, what have we learned so far in this second half of this lecture? The second half of chapter 17. We've learned to put an alkyl group on an aromatic ring, and we've learned to put an acyl group on the aromatic ring. Now we're going to look at a reaction that really doesn't have anything to do with the aromatic ring. It has to do with the group that's attached to the aromatic ring. And this is called the Clemmensen reduction. So let's suppose we took an aromatic ring and added an acyl halide. So what does that give me? So this basically adds this group to the aromatic ring. The Clemmensen reduction reaction says that if you take this compound and add zinc and HCl, now sometimes we show the zinc amalgamated with mercury. Sometimes we don't show the mercury. But this set of reagents, zinc and HCl, what it does is it turns that C double bond O group into a CH2 group. So notice what happens. Now notice the overall group. The overall reaction is that we have taken an aromatic ring and added an alkyl group to it, but we have avoided any rearrangements in the R group by doing it in two steps. We have avoided polyalkylation reactions because in the first step, we only get one group since it's a deactivating group. And then in the second group, we're not really adding anything to the aromatic ring. We're just turning the C double bond O group into a CH2 group. That's all we're saying. Okay, so don't make this any more difficult than it is. Okay, there is a limit to the Clemmensen reduction. If there's an NO2 group on the ring, the NO2 group gets changed to an NH2 group. Okay, so the NO2 group will get changed to an NH2 group. Now, we're going to look at one more reaction on page 4, and then we're going to take a little break, and I'm looking ahead, and we're going to do some little puzzles. Okay? Then we're going to, well, we'll save our little puzzles to the end. Let's just get through the reactions. If I were to take this reaction here, based upon what I know about acylation reactions, and I were to react it with this compound here, what you would say is that this does an acylation reaction in which it puts this group on the ring. And that sounds really nice, except this compound can't exist. Okay? That compound, you can't go over and get it out of a bottle. That compound doesn't exist. But what Gotterman and Koch done, okay, was they found a way to make that compound. What they said was if you took carbon monoxide and reacted it with HCl in the presence of a copper chloride catalyst. Now, if we look at these two compounds there, notice it's one carbon, one oxygen, one hydrogen, and one chlorine. One carbon, one oxygen, one hydrogen, and one chlorine. This combination of components at a very, very high pressure actually produces that compound. So the way to actually do this reaction is to mix those three together with aluminum chloride under a very high pressure, and you get this. This is called a formylation reaction because this group is called, and we'll learn this later on, is called the formal group. Okay, so this is called the Gotterman-Koch formylation reaction. So basically, what does it do? It adds a C double bond OH group to the ring. It adds an aldehyde group to the aromatic ring. Okay? That's all there is to this. Now, on the bottom of page 4 and the top of page 5, it talks about very special reactions. You're not going to be responsible for these two reactions on the test. We just need to know them just for general purposes, though. Most aromatic reactions are aromatic electrophilic substitutions, but sometimes an aromatic ring can undergo nucleophilic substitution. But this only works whenever there are very electron withdrawing groups on the ring. So notice in the example on the bottom of page 4, there are two nitro groups already on the ring. These two nitro groups are electron withdrawing groups. They are deactivating groups, and they have to be in the ortho-para position to the halogen that's going to be replaced. And then we can undergo just a simple SN2 displacement of the chlorine. Normally, substitution reactions of nucleophilic type do not occur on aromatic rings. But in this case, it does, but only whenever the halogen has very deactivating groups in the ortho and para positions. The mechanism for it, there are two mechanisms that are used to illustrate this reaction, and they're on page 5. And again, if you want to look at those mechanisms, they're really good reactions for to just as understand resonance structures, but you're not going to be responsible for those reactions. On page 6, the Birch reduction. You are going to be responsible for the Birch reduction. And on the Birch reduction, what you do is you take an aromatic ring and you add sodium metal to it, or you add lithium metal. You add one of the group 1A metals to it. And what it does is it destroys the aromaticity of the ring. And not only does it destroy the aromaticity of the ring, it gives you the least stable of the alkyl of the dienes. Notice this diene is not even conjugated. It's an isolated diene system. So not only do you destroy the aromaticity, but the diene produced is the least stable possible diene. It's the isolated and not the conjugated system. Now, the two things you have to know about this reaction: if there is a deactivating group on the ring, notice that is a deactivating group because that carbon is partially positive. If there's a deactivating group on the ring, the diene produced, the deactivating group, okay? And notice I've got it negative in my notes just because notice that it's in a basic solution. That's why it's negative. It's unprotonated in the basic solution. We could protonate it to get the carboxylic acid back. Notice that in this case, the deactivating group is not on one of the double bonds. But if it's an activating group on the ring, notice the product is this. We still get the double bond system, but notice, and it doesn't really matter, I've got it tilted over in my notes. Notice the activating group is actually attached to one of the double bonds. Now, I will leave that as an exercise to you on how this occurs doing resonance structures. Your book does a very good job of explaining why you get these two products. On the test, you will not be asked to write the mechanisms for either one of these, but I could give you this Birch reduction. And the Birch reduction is one of the few reactions or few reactions overall that will destroy an aromatic ring. This is kind of the exception to what's norm, though, okay? We look at the electrophilic substitutions, and that's where the bulk of the questions on the test are going to come from. Then we said we're not going to even worry about the nucleophilic substitution. And then we worried about the Birch substitution or the Birch reduction, which is just a very specialized reaction. Now what we're going to do is finish up these notes. Now you can see that there's just a bunch of reactions. And what you have to know is what reagents does what. Okay? Now, every reaction we've looked at up to now, with the exception of the Clemmensen reduction, was a reaction to put something on the ring or a reaction of the ring. We're going to look at a couple of more reactions right now, and these only have to do with the groups that are already on the ring. Okay, so listen carefully. On page 7, if we take an aromatic ring and let's put some groups on it, we're going to put a CH3 group here and a CH3 group taken twice here. So we're going to put a methyl group and an isopropyl group on here. The reagent CHEM20 in basic solution at 100 degrees, we also know there's water in there if it's in basic solution, at 100 degrees Celsius. So we're going to take some basic KMNOH, or KMNO4 rather. We're going to take some basic KMNO4 and we're going to boil these alkyl halides in there. What they do in this reaction is no matter what this R group is, whether it's a methyl group, an isopropyl group, a 42 carbon atom long chain, it turns it into a carboxylic acid. Now notice it's deprotonated at this time just because it's in basic solution. Then if we want to acidify it later on, okay, we can acidify it, and now notice that what happens? The R groups are turned into carboxylic acid groups. Now we don't know a way to add a carboxylic acid group to a aromatic ring, but we know how to add an R group to an aromatic ring. And now we can take that R group and turn it into a carboxylic acid. Okay, so on the test, I can give you a reaction in which you do that, and we'll look at some examples in just a second. Now, that's a way of turning an R group into a carboxylic acid. We're going to look at 3 more reactions, okay? Actually, 4 more reactions. If we have an R group attached to the aromatic ring, this position here is called the benzylic position. Remember, we talked about that before. It's called the benzylic position. It's the position of the carbon that's attached directly to the aromatic ring. This position is very special. It will undergo free radical reactions, it will undergo SN1 reactions and SN2 reactions. Okay? It undergoes free radical reactions. So if I were to just take chlorine in the presence of light, that's a free radical reaction. The most reactive position is the benzylic position. So it puts the chlorine in the benzylic position. Now, the reason that's so reactive is, notice the first step is the formation of this free radical, which is resonance stabilized. Okay? So if we take this same compound and add NBS, remember we talked about what NBS was in an earlier chapter? NBS is just a bromine free radical. What's that going to do for me? Put the bromine in the benzylic position. Notice the benzylic position is the one that's most reactive in the free radical reactions. If we take this same compound and we put a bromine in the benzylic position, let's just look at this compound here. We now know how to put a bromine in the benzylic position, or a chlorine. Then we can use this compound to either do SN1 reactions or SN2 reactions. I'll just look at the SN2 reaction on page 7. This comes in, backside attacks, kicking off the bromine. What's the product? Just a simple SN2 reaction. Now, there's one more reaction that is not on the bottom of page 7 that needs to be talked about, okay, that we have not talked about. So let me go ahead and add it to the bottom of page 7. Suppose I have an aromatic ring and I add FeBr3 and bromine. What does that do for me? That puts the bromine on the aromatic ring. Didn't we learn that in the last section on the first part of chapter 17? Anytime I have a bromine anywhere in there, remember, I can take and react that with magnesium and get a Grignard reagent. And then what can I do with that Grignard reagent? Any of the reactions that we've learned with Grignard reagents. Okay, so what can I do now? What can I do in organic chemistry? We have learned a great deal of reactions. Okay, now we're going to learn a whole bunch of reactions in Chapter 18. But what can I do now? I'm going to give you some reactions. And I know every one of you have your mics muted. Okay, so I need you all to unmute your mics and help me with this. Because what we're going to do now in just the next couple of minutes is we're going to actually look at some reactions. And these are what are called multi-step synthesis reactions. So we have to put all of our knowledge that we have together to learn to do something. So we're going to look at some reactions. I'm going to start with benzene. And I want to make this compound here. So congratulations. Let's see how to do that. Now, what did I do in this reaction? I put an NH2 group on the ring and I put a CH3 group on the ring. Do you agree I can do either one of those? Okay. Now, I've got a question. Do I know how to put a CH3 group on the ring? Yes. Do I know how to put an NH2 group on the ring? Look back through all the reactions that you covered. Can you put an NH2 group on the ring? No. But I know how to put an NO2 group on the ring. And then I know how to change that NO2 group into a NH2 group. So let me ask you a question. What do you want to do first? Do you want to put the NH2 group on the ring, or do you want to put the CH2 group or CH3 group on the ring? Somebody help me out. Kylie, which one do you want to put on the ring first? NH2 or CH3?
NH2.
Okay, so we know that if we do that, we have to first put the NO2 group on the ring. Now, looking back in your notes, you should easily be able to find that set of reactions. What puts the NO2 group on the ring? That's the nitric acid, sulfuric acid. So this is what you're going to have on your note card, the reaction of this to put the NO2 group on the ring. Now, can I at this moment in time add the group that adds the methyl group? If I wanted to put the, okay, I guess the question I'm asking, do I want to change the NO2 group into an NH2 first, or do I want to add the CH3? I think I want to add the CH3. So what adds the CH3? This set of reagents. Notice that methyl chloride and aluminum chloride would add the CH3 group to that ring. But what's the problem here? Look at the group that's already on the ring. What can you tell me about that group? Is it an ortho-para-director or a meta-director? Looking back in my notes, it's a meta-director. It's also a deactivating group. And remember, the alkylation reaction will not occur on a deactivated ring. So I was wrong. I cannot put that on first. So what do I do instead? I change this to this. And I look back in my notes, and this is the way you have to think through these problems. What changes the NO2 group to the NH2 group? That's the Clemmensen reduction. Now I have changed the NO2 to an NH2. Now can I do the alkylation reaction? Will that put the methyl group on the ring? The answer is yes, it will. And I'm looking at the group that's already on here. Is that an ortho-para-director or a meta-director? And because it has a lone pair on that nitrogen, it's an ortho-para-director. So it's going to put the methyl group in the correct position. Now, it would also put it in the ortho position, but notice I'm just wanting to get a synthesis for one of the products. Now, the second thing I have to ask myself, since this is an alkylation reaction, what's true? Will the methyl group occur on this ring? Yes, because this is an activated ring. So this reaction does occur. So notice what I can say. Here's the steps. Step 1, add this. Step 2, add this. Step 3, add that. Notice what you just got finished completing. You just got finished completing a 3-step synthesis reaction. Now let's change the problem. Okay, let's start again with benzene. And instead of making that compound, let's make that compound. Now, what do I need to do? I need to put the NO2 group on, and I need to put this group on. Now, unfortunately, fortunately, I do know how to put that group on. But do I know how to put this group on? No, but I do know what? If I can put an alkyl group on, I can change it to that. So I've got 3 steps in this. 1, put the NO2 group on. 2, put the alkyl group on. And 3, change the alkyl group to the carboxylic acid. So which steps do I do first? Okay, let's see. I want to put the NO2 group on first. So I know how to do that. Okay, so I can put the NO2 group on. That's just nitric acid and sulfuric acid. So if I do that, what do I have to do next? Put some alkyl group on here. Since it doesn't matter what alkyl group it is, I'm just going to try to add a methyl. The reagent to do that would be this. So if you did this on the test, what's wrong with that step? Again, the nitro group is a meta-director, and it's a deactivating group, so this won't occur. So I can't put the nitro group on first. So this was a poor synthesis. So what can I do? If I can't put the nitro group on, let's put the alkyl group on first. So I'm going to add my CH3Cl and my AlCl3. And add the CH3 group. Now, I've got 2 choices now. Do I change the CH3 group into this, or do I put the nitro group on and then change the CH3. Notice how I'm talking myself through this. I'm going, it's like you come to a fork in the road. Do you go left or do you go right? And once you take that fork, then the road forks again later on. So I think what I will do is I will change it to the carboxylic acid. Now again, here's where your note card is going to come into play. You should be able to now look at your note card and see that the reagent for this is KMnO4, OH minus, water, 100 degrees Celsius, and then to turn it back into the carboxylic acid in the second step, I'm going to protonate it. Now, if I do that, can I then add the nitro group? So in the next step, I would just add the nitro group. And again, the reagent necessary for this, and you will have memorized most of these reagents by the time we get to this point. But what's the problem? This is a meta director. So even if it's going to put the NO2 group on, it's going to put it in the wrong place. So this won't work. So maybe it was a bad idea to change that to the carboxylic acid. Let's try the other option. Let's take this, and instead of changing it to the carboxylic acid, let's put the nitro group on first. Now, a lot of students put this on the test and say, this will not work. But notice what's happening here. We're nitrating something with a methyl group on it. This is not the alkylation reaction. Okay, this is not the alkylation reaction. Okay, Kylie, I'm going to go ahead and mute you and everything. So we've got the nitro group on there now. Does it go in that position? Is this an ortho-para director or is it a meta director? According to my notes, it's an ortho-para director, so it will put the nitro group in the correct place. Now, can I do my KMnO4 step? So notice what we had to do. We had to do the steps in order. So that's what you need to be able to do. Now, the last thing that's not in the notes is this. We want to do something like this. We want to do a reaction where we do something like this. Now, listen carefully. I'm going to tell you that when you put a complex substituent on an aromatic ring, that's not going to be done in a single step. Students would want to take this and add some magic group to add that. And that's not the answer. Okay? I don't know what is the answer, but you can rarely add a very complex substituent over here in a single step. Now, this is where your notes from chapter 8, 9, and 10 and 11 are going to be very important. So if you don't have your note cards from chapter 8, 9, 10, and 11, find somebody that has very, very good note cards. Email each other within the course and say, hey, could you send me your pictures of your reactions from chapters 8, 9, 10, and 11? Because what this does, this part of the chapter does, and you're going to see a couple of questions on the test and a lot of questions on test 3 dealing with this, is you have to go back to all of those reactions and incorporate them into here. So my question is, how would you do something like this? Okay, what would you do to get that group onto the ring? Okay, notice what happens here. We have CH2, C double bond O, CH3. Now, I don't really know what to do. So the first thing I'm going to do is I'm going to just do something that I do know how to do. I'm going to put a methyl group on there. Now, we know how to do that. That's just AlCl3 and CH3Cl. Then I'm going to take that and turn it into a bromide. Whoops, not a bromide, sorry, a CH2Br. Because if I could put a bromine on there, I might can do some things. So then I'm going to do this, okay? I'm going to say, how did I do that? That was just NBS. Now notice how we're incorporating various reactions, and you've got lots of homework examples to deal with this. If I have this, I can treat this with this acyl ion, or this acetylene ion, this acetylite ion from a long time ago. We've seen this reaction before when in chapter 9. Now what this does for me is this. Now watch how organic synthesis actually works. Now if you look at this compound, this piece, and I'm going to erase these lines now here, and this piece is the same. And I think back to chapter 9. How can I take a triple bond and turn it into a ketone? And there were two reactions in chapter 9 that keep coming up over and over again. One is the mercury reaction and one is the boron reaction. And I think this compound was actually mercury sulfate in sulfuric acid in step 1. And I think step 2 was what? The NaBH4 OH minus. I think you can look back in your chapter 9 reactions to make certain that those are the reagents that were used to take a triple bond and turn it into a ketone. And if you remember, that went through the intermediate where we had what? We had the enol that underwent the tautomerism. So sometime between now and the second test, you need to look back over those reactions on chapter 8 and chapter 9. So notice this part was the organic chemistry that we learned in this chapter. We learned this part not only in this chapter, but way back a long time ago when we talked about NBS. I think that was in chapter 6. This chapter and this chapter were in chapter 9, or this reaction and this reaction were in chapter 9. So as you go through these reactions, notice what we can do. We can take and start making very complex molecules. Now, this step here to figure out the steps that are needed is like planning a trip. Okay, I know how y'all plan your trip. You get on Google and you get on your Google Maps and you type your destination in and you start your starting point and it prints out your map for you. But before there were Google Maps, there was actually things called paper maps. And you would sit there and you would plan out your trip going from one route to another. And depending on which way you wanted to go, you could take this interstate or take that interstate. So what you need to be able to do before the second test, and there's not a lot of these questions that are multi-step on the test, but there's at least a few points that are going to be like that. Most of them are going to be single or two-step reactions, but there will be a couple of them that are these multi-step reactions. You have to have your notes organized in your chapters 8, 9, 10, and 11 reactions, and then, the few reactions we had in chapter 14, And then we really didn't have any more reactions in chapters 15 and 16. There weren't a lot of reactions in chapters 15 and 16. And then your chapter 17 reactions. So as you organize your note cards or your sheets of paper that you're going to use for the test, you need to have those organized in such a way that you can say, okay, how can I do these type of reactions? Okay, so looking at the products, if I could get the acetylene group on here, I know that I could change the acetylene group to that. So looking at that, how do I get the acetylene group on here? Well, I know that if I had this with a bromine, I could do an SN2 reaction to get the acetylene group on there. So how do I get the bromine on there? Well, I learned that I can get the bromine on there because it's the benzylic position by putting NBS. But in order to do that, I needed the halide, the alkyl group on there. So I got the alkyl group on there in an alkylation reaction. And so what most students do with this is they do the problem either one of two ways. They usually don't start with the starting material and work their way forward. They start with the product and work their way backwards. And then I have a unique group of students who start the problem on both ends and work toward the middle. Both of those techniques work really, really well. This is sort of like those little puzzles you had whenever you used to work them in little books or whatever, where you had the maze and you had the start position and the end position. And you'd go down this route and you'd hit a dead end. So you'd erase back and then you'd find another route until you found your way through the maze. This is exactly the same thing. Suppose you got to this point and you couldn't get any further. Then you would back up a step and go a different route. On these questions on the test, though, you do not want to leave them blank. There's partial credit. So let's suppose you got 4 of these steps right, but the one step you made up some magic reagent that did not work. You're going to lose the points for that step. But if all your other steps are correct, you're going to get 6 out of the possible 8 points. And these multi-step questions usually are high point questions, so you can't leave them completely blank. Okay, so that finishes up all the reactions on chapter 17.